Hey everyone. I thought we've been kind of discussing some deep and heavy material, a lot of information, and I figured now would be a good time to actually, apply it and see how to actually do the stuff with a more complicated converter than what we were looking at before. So, today I wanted to look at this converter. And this is exactly what I said you could do with this stuff, right? So, we got this thing, we got this thing, we got this inductor, second switch, and finally the output. And this is called the SEPIC. And SEPIC stands for single-ended primary inductor converter. Now, don't ask me what the primary inductor is. I don't know, but that's what they call it. They were trying to solve some stuff with this. Who knows? It's just some crazy stuff, right? So this is what we got. And yeah, let's just begin with like labeling what our components are, right? And then eventually, what our voltages are. So I'll label our components in red, right? And so yeah, just to explain what we're doing, we're going to do the DC solution. So we learned IVSB, CCB, how to size components. We're going to do all that stuff with this, right? And we're going to plot, the conversion ratio, see what that looks like, so we can kind of get a handle on what's going on. Cool. So just for now, I'm going to label, and then we can come up with some, input and output requirements for a specific converter. Cool. So we have L1, L2, C1, C2. We have our R load. We have what I'll call Q1 and Q2. The input I'm calling VG, and the output is V out. Cool. So again, this is already much more complicated than the buck converter, right? There's already way more things going on. There's 2 inductors, 2 capacitors, but I just wanted to show you it's not so complicated, right? It's not so scary. You can just apply the things we've learned in the exact same way. Cool. So I'll just add in ground if you want to put ground in, and we won't discuss necessarily the benefits of why you might want to do this. Oh, maybe we will. We'll see what happens. This is just off the cuff. We're just going through stuff. Great. So we already know that there are 2 states, or we don't already know. I'm going to tell you. There are 2 states in this converter, right? So there's one state when time is between 0 and DTS, right? And in that state, Q1 is on, and Q2 is off. And then we have the second state, right? The second switching state. And that's between DTS and the end of the switching cycle. And in that state, Q1 is off and Q2 is on. So what we're going to do is we're going to draw the converter in both switching states. Again, we're assuming that we're analyzing this converter for steady state, right? This is steady state analysis. Cool. Okay, let's do it. Okay, so the first subinterval. We draw the converter, right? So we have our input. We have our first inductor, right? We have an inductor connected right to the input, right? And let's just go back and remind ourselves what's going on. So this switch is on, right? In the first state, Q1 is on and Q2 is off. So this is a short. Great. Then we have a capacitor. And we have the second inductor. And then Q2 is open. And we have our capacitor and our load resistor. Great. Okay, in the second state, DTSW to TS, right? So in this state, Q2 is on and Q1 is off. So what does that look like? This is an open circuit. We have our capacitor. We have our inductor again. This doesn't change. And then Q2 is on, right? So it's a short. And then we have our output. Awesome. Okay, so let's relabel things just so we're familiar with what's going on. We'll choose the voltages or the directions of the voltages and currents, right? So just to remind you, this is where Q1 was, right? Q1 is on, and Q2 is off. And here, Q1 is off, and Q2 is on. Great. So we have L1, right? And we have to define which direction the voltage is. I'm just going to assume that, it looks like current's going to flow this way, right? So we have IL1 flowing this way, IL1 of T. That must mean, right, this is a passive component, right? So the current's going to flow into the positive terminal. That's just an assumption, but that's what I'm going to choose. I'm just going to be consistent in both cases, right? So that means we have VL1 over here. IL1 goes here, right? And again, this is still L1. Great, okay. So again, we have to choose the direction of the voltage and current for the capacitor. So this is C1, this is L2, this is C2. C1, L2, C2. Cool, so again, I'm just going to arbitrarily choose the direction of the voltage, right? I'll just say that that is a positive voltage, and this is VC1. And again, the current is probably going, or I'm just assuming it's going in this one. So this is IC1, right? This is IL1, right? So you just got to be consistent with the numbering, right? If we have L1, IL1, it goes on. Great. So that's VC1. And again, I'm just assuming what the voltage is for this inductor. I'm just going to say it goes that way, VL1. Or VL2, sorry, VL2, IL2. Great. And this one's the output cap. We expect that the output voltage is this way. So this is VC2. I'm just going to assume that it goes in, IC2. So again, we have to be consistent. VC1, IC1, VL1, IL1, or sorry, VL2, IL2. Right? I hope you aren't confused by that, but if you are, I'm sorry. Stop the video, rewind, figure it out for yourselves. This is V out. This is VC2, and we have IC2. Great, okay. So we're like halfway there, right? We've labeled all the things that we want to label. Well, let's label some more things actually. There are a few more things we should label. So this is VG. And yeah, we have VG over here. What else is there? This is our load, right? We can talk about the load resistance. Again, we're modeling our loads as resistors. Our load, great. I just use a different color to change it up. No, nothing to be worried about. Great. So now what do? Well, if we think back to our plan of attack, we've drawn the converter out. We've labeled the voltages and currents. So we just have to, write out what the voltages and currents are in each switching state, right? So let's start. I used the same color for everything, and maybe that was a bad idea, but let's keep going. So let's start with VL1. VL1 in this state. Well, if we look at this loop, there's only one voltage source, right? And there's some load, so KVL, the voltage applied to VL1 must be VG. And here, I'm directly applying, we're assuming that this is a DC voltage source, so there shouldn't be any ripple on an ideal DC voltage source, but you could, in many contexts, the input is rarely a constant voltage source. There's always some variation, but here we just assume that it's constant, right? So no need to apply SRA or anything. It's just DC. Great. So in the second switching cycle, in the second switching state, it's a little bit more complicated, right? Let's just keep going on with VL1. So VL1 in the second switching state, well, we have to consider a much larger loop. So one thing we should avoid doing is relating the voltage of one inductor to the voltage of another inductor, right? The voltage of an inductor is not necessarily constant. However, the voltage of a capacitor is, right? So we want to relate the inductor voltage or we want to write the inductor voltage in terms of either voltage sources, like VG, or things that have constant voltage, that will have constant voltage across them. That would be a much better way of representing what the inductor voltage is. Otherwise, we have two things that kind of vary. It won't help you solve this equation if you express VL1 in terms of VL2. So we have a few loops to consider, or we have one loop to consider, but you could consider a second, and I will claim that second loop is wrong. So we could consider this loop. If we consider this loop, you will not get anywhere, right? You'll have VG, so VL1 will be VG minus VC1 minus VL2, which doesn't tell you, and you're relating VL1 to VL2, and again, we're trying to solve for VL. It won't work out, right? Eventually what we're going to do is draw out the inductor voltages and then the inductor currents, right? So if we have one inductor voltage in terms of another inductor voltage, it's going to be hard to draw out what that inductor voltage looks like as a function of time. We would want it to look like, a piecewise constant voltage or something, right? Like we did before with the buck. However, it's not so clear what VL2 actually looks like. So the loop we want to consider, again, we want to relate the inductor voltage to capacitor voltages and DC sources. So the loop we want to consider is actually this much bigger loop. So I'll erase this guy. The loop we want to consider is actually this entire loop. So we're going all the way here. That is the loop we want to consider, right? So VL1 in this case is VG minus VC1, and then here we have minus VC2 or V out. So it's VG minus VC1 minus VC2. And I haven't applied SRA yet, so these are, the full signals, let's say. Cool. So that's VL1. Now let's write out, let's choose another color. Let's write out VL2. Let's do all the inductors first. So VL2, in this first state, VL2, we can find VL2 in relation to VC1 by looking at this loop, right? So if you kind of shift this cap down, or if you look at this loop, I challenge you to figure it out for yourselves, but I'll give you the answer. If the positive and negative terminals were aligned in the same direction, they would be the same value. However, they're not aligned, right? They oppose each other. The positive of this voltage is connected to the negative of this voltage. So that means the inductor voltage must be minus VC1. Cool. All right, VL2 in this state, VL2 is equal to, well, we have a different loop now, right? And here, again, there are two loops to consider. This first loop, the one we were thinking of before, this first loop would relate VL2 to VL1, which is what we don't want to do, right? It would be an under-constrained problem, kind of. So the loop we want to consider in this case is this loop, right? And it's easy to figure out what the inductor voltage is because there's only one other voltage in this loop, if we think about this loop here. And that voltage is VC2. So in the second state, VL2 is equal to VC2. Cool. Now, capacitor currents. So IC1. IC1 in the first state. Well, we can kind of tell what's going on, right? The inductor and capacitor are connected here, as we noted for this previous equation. So that means that the current passing through the inductor must be the current passing through the capacitor, right? It's a single loop. So IC1 must be equal to it must be equal to IL2, right? Because the loop, I've defined the current to go in this direction. This current flows in the same direction as IC1. Cool. So IC1 is IL2. And in the second state, IC1, IC1 well, in this case, it looks like it's a little bit more complicated, right? We can kind of think about two nodes, right? There's this node, and there's also this node, right? So what current is the capacitor C1 exposed to? Well, if we look at this node, then we have to kind of consider the current flowing this way and the current flowing this way to figure out what IC1 is. However, if we look at this other node, there's no current flowing here, which means that we know that the current flowing through the cap, flowing out of this branch, must be equal to the current flowing into this branch, which is IL1, right? So IC1 is equal to IL1. Cool. Now, IC2, right? IC2, what is IC2 equal to? Okay, well, in this first state, we have a single loop. So the current flowing out of this capacitor, right? Consider the direction I've decided that the capacitor current flows. I'm saying it's flowing down. We know that if we apply voltage to a resistor, then the current must flow from the positive terminal to the negative terminal. So the current is flowing in this direction. This is V out over R load. And it opposes the direction of the current I've indicated for IC2. So IC2 in this case must be equal to minus V out over R load. In this state, in the second state, IC2, now we have a current flowing in here, right? So what is this current? Okay, well, we have to kind of inspect this node, right? So as in the previous case, we have some current flowing out, again, V out over R load. And we have some current flowing in, right? So what is this current that's flowing into this node? Well, it's this current which comes from here, right? So what current is flowing here? Well, we already said that IC1 is equal to IL1. So IL1 is definitely flowing in from this branch, and IL2 is flowing out of this branch. So this current, whatever it is, must be the difference of IL1 and IL2. So it's IL1 minus IL2 is flowing in. And then what's flowing out is V out over R load is flowing out, minus V out over R load. Cool, so those are all the voltages, right? That we've figured out what all the voltages and all the currents are in this circuit, in both switching states. So we're almost ready to apply IVSB and CCB and solve this converter, or solve the DC solution, provide the DC solution for this converter. What we do have to do is think about small ripple approximation, right? We have to think about what voltages and currents we can consider to be small. Okay, so this is the DC converter. We expect that the output voltage is constant, right? So we expect, or we design the output voltage right? I said this before. So we expect the output voltage to be constant because that's how we're designing it to be. So for sure we can say that VC2, we can apply a small ripple approximation to VC2. And for this case, I'm going to assume again that VC1 is also constant, right? We'll assume small ripple for VC1. And we'll see what happens, right? We'll see what happens if we do that. So let's apply small ripple approximation. So the voltages we're going to assume are constant, but the inductor currents we will not assume are constant necessarily. So we don't need to do anything here. So it just goes to VG by SRA. Here both of these go to constant, so by SRA we get VG minus VC1 minus VC2. VC2. Next. This we're assuming goes to a constant by SRA, right? So we have minus VC1. And this one again, VC2, you can apply this directly, it goes to VC2. Okay. IC1, this is an inductor current. We're not assuming that small ripple can be applied, so nothing happens. However, V out, which is actually, maybe I should have said this, specified this before, but again, V out and VC2 were the same voltage, right? They're connected by a short, they're the same voltage. So really I should have written this as VC2 over here and VC2, right? Then it kind of makes a bit more sense to you guys, I hope. But again, VC2 is a voltage. We're going to assume that we can apply a small ripple approximation. So that means that this goes to VC2 over our load. And this These do not change. IL1 and IL2 are not constant. We're not assuming those are constant. We are assuming, however, that VC2 is constant. So it goes to IL1 minus IL2 minus VC2 over our load. Great. We're almost there. We're just going to have to redraw a whole bunch of stuff so that it's easier to see what's going on. Okay, well, maybe we'll do that later. But next, we apply IVSB. So we have to do IVSB for L1. So let's do that, right? What it says, what IVSB says, is that the average of the voltage applied to the inductor over one switching cycle is equal to 0. So if you write out this integral directly, and we can do this, and I will do this, however, it becomes very tedious, and there's a kind of a shorthand way you can write this out. So we'll split this integral up into two subintervals, right? So from 0 to dts. So in the first subinterval, the inductor voltage is equal to Vg. And in the second subinterval, the inductor voltage is equal to Vg minus Vc1 minus Vc2. Great. And this is equal to 0. So we can kind of ignore this thing, right? We can get rid of the TSW. And if we integrate this, sorry, we don't get rid of it. We actually divide everything out by TSW. So let's write that out. So 1 over TSW, and then we perform this integral. This is a constant, right? So we can pull it out. So in the first subinterval, we get Vg times dTSW. And in the second subinterval, we get, all of these are constant, so we get Vg minus Vc1 minus Vc2 times 1 minus, or TSW minus dTSW. All right, and this is equal to 0. If we divide everything by TSW, then we get dVg plus d prime, right? So we divide TSW out by the second thing, right? The second term over here. So this turns to 1, this turns to d, which is 1 minus d, or d prime, right? So in the second subinterval, d prime times Vg minus Vc1 minus Vc2, and that is equal to 0. And what I want to point out is that this, it's kind of, maybe it's lazy, but it is definitely more convenient to simply, especially when everything is constant, to simply write the voltages times the period in which they're applied, right? So no one's going to be, well, maybe someone will be mad at you, but I won't be mad at you if you simply write d times whatever voltage is applied in the first state plus d prime times whatever voltage is applied in the second state. To me, that's a perfectly reasonable way of figuring out what IVSB is for L1. So please, go ahead. Basically, all it does is skips directly to this step without doing this integral stuff. For you guys, doing it for you guys, I hope you appreciate this extra time I'm spending. Cool, so we can simplify this, right? So d plus d prime is 1 for Vg. So if we simplify a little bit, we get Vg minus d prime Vc1 minus d prime Vc2. And that is equal to 0. So that's as far as we can get right now. That's kind of too many unknowns, right? We don't know what Vc1 is, and we don't know what Vc2 is. Okay, so let's do IVSB for L2. Maybe this will give us some more information, right? So again, IVSB for L2 says that the average voltage applied to the inductor over one switching cycle is equal to 0. If we write this out explicitly, what we get is that from 0 to dTSW, let's look back, we apply minus Vc1. And for dTSW to TS, we apply, what do we apply? We apply Vc2. Cool. And that is equal to 0. And again, we can write out the integral, or we can just say, as I said before, we get minus d Vc1, right, plus d prime Vc2. And I hope you can see how I did that. And if not, please feel free to do the integration yourself. You know, pause the video, take some time. No big deal. Okay, so we have it. We have a second equation. So what I'll do is I'll label this equation 2, right? So that's equation 2. This is equation 1, right, over here. So we have two equations. We have two more things to do, right? We have two more CCBs to do. So let's do those first before we take a step back and see what's going on. So we're going to do CCB on C1, right? And what this says is the average current applied to the capacitor over one switching cycle is equal to 0, right? Because we're operating in steady state. So maybe I'll just take it really fast and really loose here. So what this is saying, again, we're not applying SRA, but we are averaging. So maybe I will write this out explicitly, just so that we're clear on what's going on. So in the first state, 0 to DTSW, we're applying IL1, right? I hope we're applying IL1. Let's look. We're applying IL2. We're applying IL2 in the first state. Cool. In the second state, second switching state, from DTSW to TSW, we're applying IL1. Great, right? And again, what we can't do, this is supposed to be equal to 0, right? What we can't do is apply small ripple approximation. What we can say is that this is actually D times the full average of IL2. And this thing is D prime times the full average of IL1. And 100%, it just took me a few seconds, it is not immediately clear why this would be the case, but it is indeed the case that this is what's going on. And we'll see from the waveforms that this actually works out, and you can do simulations. Well, maybe I'll figure out how to help you guys out with some simulations so you can appreciate this more deeply. But what I want to point out with this is that this, if you combine it with this term, right, if you multiply this in, this thing is the average of IL2, and this thing is the average of IL1. That's what I want to point out. What this is saying in the end, if you write this out, is that D times the average of IL2, plus D prime times the average of IL1 is equal to 0. And there's probably a more precise way of writing this, but this is what CCB of C1 is telling us. The average of IL2 times D plus the average of IL1 times D prime is equal to 0. So IL1 and IL2 are related in some way. Cool. So let's do the final equation. Just to remind you, this is equation 3. Right? That's equation 3. And now we're going to do the last one, right? We're going to do equation 4, which is CCB for C2, or the output capacitor, right? So again, what this is saying is that the average current applied to C2 over one switching cycle is equal to 0, right? And if we're operating in steady state. And if you write this out, again, I'm going to use the same tricks that I did here, except in this case, if we go further back, right? So in the first switching state, we have minus VC2 over our load, or minus V out over our load, right? The load current, I out. And here, we're going to have like the average thing that we did before. So D prime times IL1 minus D prime times IL2 minus V out. Cool. So if we write this out, in the first switching state, I'll do it in this shorthand way. We get minus V out, or minus VC2, whatever you want. I'll keep it as VC2 just so we're all clear. Minus VC2 over our load in the first switching state. And in the second switching state, D prime times, again, minus VC2 over our load. And what else do we have? We got IL1 minus IL2. So plus IL1, the average, plus the average, right? The average, this is D prime, plus the average of IL1 minus the average of IL2. This is the DC solution, right? So we're looking at, it's only going to tell us the DC components of our signals. So this is equation 4. So now we have all the things we need. So what do? Well, we have 4 equations and 4 unknowns, right? We want to know what the average of IL1 is, the average of IL2, the average of VC1, and the average of VC2. So to do that, well, we have 4 equations, 4 unknowns. We combine them in order to solve, right? So the first thing we'll do is we'll combine 1 and 2. Equations 1 and 2. That will give us what the voltages are. So from 1 plus 2, let's see what we get. I don't mean plus direct plus, I just mean, you know, and. I mean this as and. Let's do that. 1 and 2. So what do we have? We have Vg minus d Vc1, or d prime Vc1 minus d prime Vc2. Let's just rewrite it so we can see it over here. Vg minus d prime Vc1 minus d prime Vc2. Vc2 Vc1. Let's just make sure I got that right. Minus d prime Vc1 minus d prime Vc2. Great. And the second one, this is equal to 0. 2. What is 2 saying? 2 is saying minus d Vc1 plus d prime Vc2 is equal to 0. Did I get that? Okay, good. My Vc2 is equal to 0. Okay. So you can kind of see like what we're going to do, right? This is relates Vc1 to Vc2. So we can, you know, rewrite this in a slightly different way. dVc1 is equal to d prime Vc2. Right? Here we have a d prime Vc2. So we can replace this thing with dVc1. So if we stick this in here, then we get Vg minus d prime Vc1 minus dVc1 is equal to 0. And we can combine these, right? So d prime plus d is 1. So we have Vg minus Vc1 is equal to 0. Or Vc1, the average voltage of Vc1 is equal to the input voltage. Whoa, crazy. We found the solution, right? And consequently, if we plug this back into this equation, then we get, so we bring this back into equation 2. Maybe I'll use a different color so you can see. We get d, Vc1 is Vg, is equal to d prime Vc2. Or Vc2, which is equal to V out, by the way, is equal to d over d prime, the input voltage. So what this is saying is that the conversion ratio of this converter, the SEPIC converter, is d over d prime. Great, we solved basically everything, right? We know what the we know what capacitor voltage C1 is, and we know what capacitor voltage C2 is. Super cool. We found the conversion ratio. This is like a big part of understanding switch mode power supplies. So let's look at this graph, right? Let's look at the conversion ratio as a function of d. So this is m of d. And maybe it'll be good to write this out like without this d prime thing, just so it's a bit easier to understand what's going on. Okay, so d can only vary between 0 and 1. So we have 0 over here, and we have 1 over here. And let's just put 50%, 0.5. D can be 0.5. Maybe we got a quarter, right? We'll evaluate a few different points to see what this plot looks like. Okay, well, at d equals 0, m of d is 0, right? I hope you can see that. We'll inspect some other things a bit more deeply. So at d equals 0, m of d is 0. So what is m of 0.5? Well, we got 0.5 over 0.5, right? 1 minus 0.5 is 0.5, which is 1. So operating at a duty ratio of 50% gives us 1. So it's somewhere here, right? And what is, let's see what 0.25 looks like. 0.25, well, that's 0.25 over 0.75. What is that? That is 1 over 3. I hope that's 1 over 3. It looks like 1 over 3 to me. So 1/3. So it's a smooth function. It doesn't appear to be, we can see that it's not linear, right? So we're going to connect that smoothly. Okay, what is m of 0.75? Well, it's 0.75 over 0.25, right? Which is 3. So, well, my scale is way off, right? Let's rescale this. Let's rescale this so we can fit it all in. So let's say 1's here, right? I should have known that this was the case, right? I should have known that it was going to look like this. because I know what this looks like. I should have been prepared, but I wasn't. It's my fault. Okay, so we have a third at 0.25, we have 1 at 0.5, and at 0.75 we have 3. So 1, 2, 3. It's somewhere up here, right? At 0.75 it's 3. Okay, what happens at 1? What happens if d equals 1? Well, it's 1 minus 1, which is infinity, right? So this tends towards infinity. Somewhere over here tends towards infinity. So this plot... Whoa, guys. Whoa, what's going on? So this plot is unerasable, but this plot, if we connect it, starts at 0 and goes up to infinity. As we approach 1, our conversion ratio gets higher and higher, right? And this is kind of interesting, right? So for the buck, we were only able to step down the voltage, right? But for this converter, the SEPIC converter, we're actually able to, so for some Ds, so when D is less than 0.5, we step down. Or we buck. And when D is greater than 0.5, we step up. Or boost. Right? And for that reason, we say that this has buck boost functionality. It can both step up and step down. And that seems kind of crazy, right? Like, remember back to the voltage divider, where I said that the voltage divider can only step things down. Like, what happens if we need something bigger than the input voltage? Well, this is something you could use to do that, right? This thing can increase the input voltage to something greater than whatever. So you have 5 volts at the input, you can make it as high as you want. Well, not really. You can't make it as high as you want, but you can make it bigger. You can make it bigger than the input voltage. You make the output bigger than the input voltage. And that's a huge benefit, right? That allows us to do a lot of different things. And that this converter has that ability. Some converters only have the ability to step up voltages. And the base one is called the boost. Maybe I should have done the boost, but I wanted to do something more complicated. And this, applies all of the techniques we were talking about before in a really nice way, so I wanted to do it. But this thing can step up and step down. Cool. So this was, using equations 1 and 2. Let's look at equations 3 and 4. Right, so the first two equations, they were equations regarding the volt-second balance. These ones are about capacitor charge balance. So these are going to tell us something about the currents, right? They were equations relating the currents. So let's rewrite them so we can solve it more easily. So equation 3, D times IL2, the average of IL2, plus D prime times the average of IL1 is equal to 0. So D times the average of IL2 plus D prime times the average of IL1 is equal to 0. Okay? Equation 4. Oh, did I not did I not write this out in a better way? I'm so sorry. So what do we have? We have D prime IL1 minus IL2 is equal to VC2 over our load. So the sum of these two currents, or the difference between these two currents, times D prime is equal to VC2 over our load. Great. So D prime IL1, maybe I'll write it out like this, minus D prime IL2 is equal to VC2 over our load. And we kind of know what this is, right? We know what it is as a function of VG. We already solved for this. This is equal to D over D prime VG, right? So we'll sub that in later. So first, let's just solve for this, right? So this equation gives us a direct relation between the first two currents, right? So let's see what's going on. Let's rewrite this. Sorry, let's rewrite this, right? D times IL2 is equal to minus D prime times IL1. Well, we have a D prime IL1 over here. So we can replace this with minus DIL2. So we have minus DIL2 minus IL2 minus d prime IL2 is equal to d over d prime Vg, or over our load. Right, I just subbed this in. Or Vc2 over our load. D plus d prime is 1. So what this says is that IL2 is equal to, the average of IL2 is equal to negative Vc2 over our load. And this negative is important. What does this negative mean? Well, let's look back at this, where we like defined what the directions of the currents were, right? So here I assumed that the current was going down, but this negative sign implies that it's actually going up, right? And a negative current means that it is actually pointing upwards, right? If we chose the current to point upwards instead of downwards, we would have had a positive sign in the end. But here, my choice was the other way, so this is what the average IL2 is, minus Vc2 over our load. Okay, cool. So we know what IL2 is. Let's look at IL1, right? We can solve for IL1 simply by plugging in this information, right? We already have a relation between IL2 and IL1. Let's plug this back in, right? So IL1 must then be, right, if we just stick this thing back into here, then what do we get? We get minus, so let's be precise about this. We have D times minus Vc2 over our load, in other words, the output current, is equal to minus D prime IL1, which means IL1 is equal to D over D prime times Vc2 over our load. Very interesting. Cool. So we kind of see this is the conversion ratio we saw before, right? Let's erase that. This D over D prime is the conversion ratio we saw before, and it pops up again, right? This same relation, right? This reminds us of M of D, right? So it's all kind of connected, right? The relations between the currents and voltages all seem to be related to this duty ratio. Cool. So this is, we found the currents, we found the DC currents and the DC voltages. Now what do we do? Well, now let's draw out the waveforms, right? We're an hour in, let's keep going. However long. Okay, so how do we do this? Well, sorry, excuse me. First, we draw out the voltages of the inductor. Then we draw out the current of the inductor. All right, let's go all the way back. Inductor voltages, or voltages applied to the inductor, and then we can draw the inductor current. So we have to do both voltages to find both currents, and then we can find the capacitor currents and then the capacitor voltages. So let's do that. So this is VL1. And then this is IL1. Again, this is all a function of time. And we're looking at one switching cycle, right? for both of these, one switching cycle. And there are two subintervals, right? So DTS, TS, DTS, TS. Right, chugging through this problem. Doesn't it feel good? It feels great. I'm loving this. Haven't done this in a while. So we have VL2 and IL2. So let's get to work. Let's figure out what's going on. So in the first switching state, the first interval, the voltage applied to the inductor, right? We should look at this. The voltage applied to inductor L1 is VG. Right, I'm going to be flipping back and forth. I hope you don't mind. So in the first switching interval, we have VG. In the second switching interval, we have something that's a bit more complicated, right? In the second switching interval, it's VG minus VC1 minus VC2. Okay, well, we know what VC1 is. We know what VC2 is, right? So VC1, incidentally, VC1 is equal to VG, right? So we can already kind of cancel these out. So VG minus VC2. VC2 is V out, right? So we could just write V out. And this is equal to d over d prime, or minus d over d prime, VG. Great. And let's look at VL2. So VL2, in the first interval, we apply minus VC1. This is the input voltage, right? VC1 is VG. In the second interval, we apply positive V out, right? So this is kind of the opposite. First, we apply a negative voltage, and then we apply a positive voltage. So, first subinterval, we have minus VG. Second subinterval, we have VC2, which is V out, right? Which is d over d prime VG. Cool. Well, these lines are funky. Let's keep it all straight. Let's keep it all, like reasonable lines that you can actually read. Okay, so we have these two subintervals, and so basically we know some information about the slope of the inductor currents, right? This is like L2 dIL2 over dt, and this is L1 dIL1 over dt. So this is telling us that in the first portion of the subinterval, or the first portion of the switching cycle, IL1 is increasing, and then it's decreasing. Here in the first portion, the IL2 is decreasing, then increasing. And we know some information about the averages. So the average of IL1 is equal to d over d prime VC over R load, VC2 over R load. Right? And there's actually, so this VC2 is actually d over d prime times VG. So in other words, we get this square relation with d over d prime to IL1. So the average is some positive value, d over d prime squared times VG over R load. Great. So that's what the average is. D over d prime squared, VG over R load. The first subinterval, it's increasing, right? We're applying positive volt seconds. And in the second subinterval, it's decreasing. We're applying negative volt seconds. So VG over L1 is the slope. And minus, we're going to write d over d prime VG over L1 is the negative slope. Great. So again, this is kind of what I was saying about the constant, how we can kind of think about the d times the average instead of integrating from 0 to dTs of IL1, right? Because they're like this inductor current, we expect it to have some continuous average over the whole thing. It's just that there is some ripple on top of it. So the area of, I guess what I'm highlighting actually is that the area under this you might call it a trapezoid. The area under this trapezoid is actually equal to the area under this rectangle, right? Because the current goes below the average equally to how much it goes above the average, right? So what I'm saying is that this little triangle, the area of this little triangle, is actually equal to the area of this little triangle. They're similar triangles. I haven't drawn them as similar triangles, but indeed they are similar triangles with equal area. Right, so it all comes out in the wash. Basically, we can say D times the average of IL1 because of this fact, because the current looks like this. It doesn't have some crazy shape. By SRA, we're assuming it looks linear in the end. Great. So what's going on with IL2? IL2. Well, what is the average of IL2? The average of IL2 is minus VC2 over R load, but again, this is actually equal to minus D over D prime VG over R load. And I like to do it in terms of VG instead of V out, because this is more of a variable, right? We can control what VC2 is, but VG is what's given to us. So usually we like to express the currents and voltages in relation to the things that are given to us, right? The input voltage is usually what's given to us. So we would prefer to write how the voltages and currents are going to be in proportion to that thing, right? Because if that changes, then everything else will change. So IL2 is a negative value, right? So what I should do is draw this below the axis, right? So the average is minus D over D prime VG over R load. I didn't use my color, I'm so sorry. So the color we were using is this. So in the first subinterval, it's decreasing, right? It's going down. And the second subinterval, it's going up. Cool. And the slope here is minus VG over L2, right? Because we're looking at the second inductor. And here, the upward slope is D over D prime VG over L2. Great. So we've drawn out the inductor currents. Now, next step, capacitor voltages. Cool. So how do we do this? Well, we draw the capacitor currents, right? And the reason I'm drawing them with an axis in the middle is because if CCB is true, then they should have equal positive and negative portions, right? The areas under the curves of the positive portion should equal the areas under the curves of the negative portions. And then we can draw out their voltages as a function of time. And these should be constant, right? They shouldn't go positive and negative. They should just be positive or negative. So these are all functions of time. We're looking at one switching cycle. And in each switching cycle, there are two subintervals. And I highly encourage you guys to, do this with me. Write these graphs out, draw this stuff out with me as you do it. Make it as neat as you want. Or use the colors you want to use, do your thing. I'm just here to explain what I'm doing so that you can understand. But it's up to you to figure it out for yourself. Cool, so IC1. So what is IC1? Sorry, in the first subinterval, we apply IL2, right? Right here, IL2. We apply IL2. Again, this is varying with time. So it's IL2 applied for the first subinterval. Let's go back here. So we apply IL2 to IC1. So there's some, whatever IL2 is. IL2 is this thing. We're applying IL2, this portion, right? We're applying this thing to IC1. So that means that IL2 looks like this, right? It looks like, again, the average is, what was the average here? Minus D over D prime, VG over R load, minus D over D prime, VG over R load. There was some slope, right? The slope was minus VG over L2. That's the slope here. We're just copying this over, right? This is literally the inductor current, minus VG over L2, right? So that's what's applied to IC1. Well, that's what's applied to C1 in the first subinterval. In the second subinterval, what is it equal to, right? Well, let's go back all the way to the beginning. In the second subinterval, we're applying IL1, right? So IL1 is this thing in the second subinterval. It's this negative sloped thing. That's what we're applying to C1 in the second subinterval. So IC1 looks like this, right? And the average is d over d prime squared, Vg over our load. D over d prime squared, d over d prime squared, Vg over our load. Great. And there's a slope, right? This thing has a slope. The slope is d over d prime Vg over L1, d over d prime Vg over L1, right? And these things connect, right? This doesn't have to be a continuous current. It can be a discontinuous current. And in fact, it is a discontinuous. It's discontinuous, right? It's all definitely continuous, but it's jagged, right? There are these sharp edges to it. And that's totally fine because it's a capacitor current. Capacitor currents can change instantaneously. This is the information of the derivative, right? So the derivative can change quickly, but the voltage of the capacitor cannot change instantaneously, let's say. So this is C1, dVC1, the derivative, right? Some scaled version of the derivative of the capacitor voltage. So what is VC1 then? I really hope that I did. So VC1 is a function of time. We know what the average is, right? The average is VG, right? Let's just go back and look at it again. Stare at it intently. Right, so and let's see if I can find it. Right, the average of VC1. It should be somewhere here. Right, I really hope it's here. It's right here. Right, so the average of VC1 is VG, positive voltage. Great. So it's the input voltage in the first subinterval. Right. So to find out what this waveform is, I'm not expecting an explicit formula for the waveform of VC1. I'm just gonna, all I want to know is what the shape looks like, basically, right? That's really what we care about, and hopefully we have something that we can integrate easily, right? To find out what the variation or the peak-to-peak ripple or the average-to-peak ripple of the voltage is, and we can do that here, right? We can look at the charge that's applied to the capacitor here. That's easy to do. So the waveform, we just kind of want a picture of what the waveform looks like. Well, we expect, when we integrate a linear function, right? This is a linear function. When we integrate a linear function, we expect a quadratic function. So we expect something quadratic here. It's negative, right? And it's quadratic. So what's going on? So here, the derivative is negative, right? So it's decreasing. But here, it is more negative. The derivative here is more negative, right? Which means that it's decreasing more. The slope is more. So it's going to have, there's going to be some negative slope, right? Somewhere here, and the slope is decreasing, right? And we have some negative slope. So we have a quadratic that looks something like this. And then we suddenly start applying a positive, right? A positive current. So we're charging it up. So there's going to be a cusp here, right? There's going to be a cusp at this point. But the voltage itself doesn't change quickly. It's just the derivative changes quickly. So here we have a positive. We have a positive slope, and we go towards a less positive slope, right? So that means the slope is positive here and less positive, right? So it's going to look something like this, right? And then it repeats back, connects back to itself. So we have this weird cusp thing going on. Goes down. We get a little cusp over here. Everyone likes cusps. Discontinuity, and it's not really discontinuity, it's just, the derivative isn't smooth. Right, so this is what the waveform of the capacitor voltage looks like. So what I want to note to you guys is that the ripple actually isn't evenly distributed over this thing. The average isn't exactly in the middle. So maybe that's the wrong way of saying it. No, that's the right way of saying it. So what we're going to be interested in here is actually the peak-to-peak ripple. That's VC1. Delta VC1 peak-to-peak. That's what we're going to be interested in this thing, right? And that's what we'll find when we integrate this area. We'll do that later. Right now we're just drawing the waveforms. Cool. So over here, I thought this was going to be a short video, but it turns out it's just as long as every other video I've done so far. I really want to change that up, but these problems take time. It's not so easy to get through this stuff, and then breaking it up, who knows? Who knows? I'm having a good time. Okay. So IC2, we're IC2. Let's keep going. VC2. This is what we're doing. So IC2 in the first subinterval, What is it? We're drawing some constant voltage, or yeah, some constant current out, right? V out over R load, the output current. That is constant. We're assuming that the output voltage is relatively constant. Again, we'll see that it's not so constant. That's what we're plotting. But that we're assuming that it's relatively constant, which means that we're drawing a constant current, the load current, out of this capacitor. And it's negative, right? It's negative. So it's going to be down here. This is minus D over D prime VG over R load. This is the current that we're drawing out of the cap. Cool. Okay, so what's going on in the second half? This is kind of the more interesting thing to discuss. In the second half, we're drawing out V out, VC2, right? VC2 over R load. So again, the same thing. We're still drawing the load current out. And then we're also putting in IL1 and taking out IL2. So what does that look like, right? That seems kind of confusing, right? So plus IL1 minus IL2. Well, in this case, it actually kind of works out nicely, right? Because we're subtracting IL2, but actually it ends up going positive, right? Because it's negative. So we're adding these two linear functions, right? We're basically adding these two linear functions together, this one and this one. So when you flip this over, right, you can imagine that this is like the negative IL2 over this subsection. So we're adding this to this. When we add two linear functions together, we get another linear function. That is what we expect to see. And it's going to be that linear function subtracted, or minus I out. So whatever IL1 plus IL2 is minus V out. So we expect to see something that looks like this. And this is a little bit more difficult to draw exactly. And why is that? Well, we actually haven't really defined the slope very well. So first of all, what is this average? First, we should find what this average is, because that would be great. So the average, well, it's minus D over D prime VG over R load. All right, that's 1. And then what's IL1? The average of IL1 is D over D prime squared VG over R load. And the average of IL2 is D over D prime VG over R load. So let's just take stock of what's going on. So we have minus D over D prime VG over R load. And I'll just erase this for now, so it's not so confusing. So this is the first component, right? This is the load. This is the load resistor drawing something out. Then we're injecting IL1. So the average of IL1 is D over D prime squared VG over R load. And we're subtracting IL2, right? And IL2 is D over D prime VG over R load. So there's a minus sign here, right? So we're really adding it. We're putting it in. So there's a square here. D over D prime. Right, so, well, first of all, we can simply cancel those out, and all that we're left with is this. So the average is D over D prime squared VG over R load. So that is the average. Great. However, this slope is a little worrying. Right, there's a few things. I'll just clean this up. So there are two situations that could happen. Right, one situation is that this slope is always above 0, right? And that would be fine, right? Because everything is positive. However, what could happen is that the slope is not always above 0, right? Or the inductor current in the second portion is not always above 0. Maybe it looks something like this, something crazy, super high, this really crazy triangle. And there's this little portion, right? This little portion over here where we're actually taking charge out of the capacitor. And that would look different. So what I'll do now is assume that the ripple is constrained such that this isn't the case. So what does that mean for the capacitor voltage? Well, this is the slope, right? So we have some average here. The average is simply d over d prime Vg, d over d prime Vg. In the first subinterval, it's negative, right? The slope is negative. So we're decreasing, right? And in the second subinterval, well, this should be quadratic, right? The voltage slope should be quadratic because this is linear. So it's positive, it starts more positive, it ends less positive. So it goes something like this, right? Similar to how we argued that one out. So that's what it looks like if the slope is always above 0. However, if the slope is not always above 0, what we tend to see is something a little bit different. So if the slope goes, if the slope touches 0, if the current touches 0, then we expect 0 slope, right, at the very end. If it goes below 0, then we expect actually it to go negative a little bit. So if the slope is large enough that the inductor current goes negative, then what we end up seeing is something that looks more like this, right? We see more of the quadratic, right? We see it actually go negative, go down a little bit in the second portion of the switching cycle. And that means that the current will start a bit lower over here. In any case, this is what we got. We got some slope here, but the way we're going to find the ripple is by integrating this thing, right? Finding the area end of this curve. Cool, so that is the next step. Well, this is just going on forever, right? It's super long. So now we find ripple equations. Ripple equations. Man, it's got to be hard for you guys if the guy making the video is getting tired of how long the video is. Like, that cannot be entertaining for anybody. Okay, so what do we have? What do we have for the ripple equations? Okay, so we want the inductor current ripple. The inductor current ripple is easy. So IL1. L1. So what do we know? We know that slope is rise over run, right? Slope equals rise over run. So this is how we're going to find the inductor current ripple. So the rise is 2 delta IL1. The run is DTSW, right? Just going back to this thing. This is what we're looking at. And the slope is Vg over L1, right? Super simple. So what this is saying is that we can size the inductor with this equation, right? Okay, so that's one equation. L2, again, slope is rise over run, which means that 2 delta IL2 is equal to, let's look back here, is equal to over DTS, right? And we only really care about the absolute value, so let's just think about the absolute value of this business, right? It's going down, but we know that the ripple, whatever, it's going to be negative ripple, so to speak, right? It's going down, but who cares, right? The slope is Vg over L2. There's no negative inductor, so we're going to have a positive inductor in the end. That's the thing that's going to constrain the ripple. And it means that L2 is equal to 2 delta IL2 over Vg times DTS. Super simple. These are easy equations, right? This looks exactly like the buck. Great. Now we have to do the capacitor voltage, right? So C, let's use a different color. C1, right? So for C1, what we're going to do is the peak-to-peak voltage ripple is equal to delta Q, positive or negative, whatever you want to say, positive, we could do either one, over C1. So delta Q positive, and for sure there's an E at the end of positive. Delta Q positive for this guy is just the area under this curve, right? And the area under this curve, right, is just the average, it's the area of this rectangle, right? Similar kind of argument to the inductor current thing, right? There's a linear current that passes through the average in the middle. The area of this triangle is equal to the area of this triangle. So that means that the area of this trapezoid is actually equal to the area of this rectangle. So the area of the rectangle is dts times the height, right? Base times height is the area of this rectangle. So dtsw times dvg over d prime r load. Right? dtsw times d over d prime vg over r load. Right? So it's a current dependent, r load dependent. Right? So we have C1 is equal to d over d prime. So d squared over d prime, Vg over r load times Ts over the ripple we want to constrain. How big we want the ripple to be. Delta V1 peak to peak. Simple, right? That was pretty easy. And now C2. Delta V2 peak to peak is equal to, well, it's the Q negative, let's say, over C2. Right? Q negative, delta Q negative. Again, we just have to look at the current, the charge injected into the cap. Right? So again, there's a difference here. This is why I was saying it was a little bit more complicated. Because if this goes negative, right, if this current in the second portion goes negative, then we have to take into account this little triangle. If we don't assume, if we assume it doesn't go negative, then we just have to look at this square thing, right? And the square thing is easy. And that's what I wanted to do. So that's what I do. So there's two possible equations, but the square thing is dts times d over d prime vg over r load. Seems right to me. Seems right to me. Cool. Okay. So then that means that C2 is equal to d squared over d prime Vg over r load Ts over delta V2 peak to peak. And again, we have the same kind of relation, right? So if the more we want to constrain these guys, the smaller we want the ripple to be. Well, I totally screwed this up. So the smaller we want this ripple to be, and I recopy this answer down. The smaller you want this ripple to be, right? So this is the average to peak. The smaller you want the ripple to be, the larger the components have to be. The smaller you want, the faster you switch, the smaller the components will be. The slower you switch, the lower the switching frequency, the larger the components will be. It's the same kind of concept, right? The general concept is there. It's just that the equations look a little bit different. And specifically, this equation only holds if delta IL1 plus delta IL2 is less than the average of IL1 plus. I guess it should actually be. Let's do it precisely. D over d prime Vg over r load plus IL1, right? The average of IL1 minus the average of IL2, right? This equation only holds if this is true, right? If this ripple is smaller than this average, then we're good. If it's bigger than that average, then this equation will change. This equation will look a little bit different. And this video is already an hour and 20 minutes long, so that is the end. And I'll do more of these tutorials to give you guys a hand. But right now, that's all I got. Thanks.